Do we have homework this week? This was okay?
We don't.
But this is.
Right, that old reverse psychology. Okay, guys. So, you have homework due. There won't be another homework assignment for next week because you'll be studying for your exam. The exam will be by popular demand, or at least non-popular protest, a take-home exam. And so I'll distribute that after the problem session, which will be a review, time for more review, on Friday, a week from Friday. And then when we do in class the next Tuesday. All right. I will discuss more the rules of the game when the time comes for what's allowed and what's not allowed relative to the take-home. But Rex will come back to that. So the exam covers essentially the material in lecture notes 8 through 16. And the associated podcasts are there. And through the problem set that's due today. Yeah?
Your notes weren't posted for from October 30th onwards.
Which one?
From October 30th, which is last Thursday, the notes aren't posted.
Not every lecture has, in terms of the date, has a lecture because we don't cover all the material in one. Sometimes just a podcast because the lecture notes extend over multiple days.
Oh.
Okay. So, all the notes have been posted at this stage. So that includes the discussion of quantum dynamics, that is Heisenberg picture, Schrodinger picture, adiabatic evolution, sudden evolution, all that kind of stuff. The wave mechanical representation in quantum mechanics, position and momentum space, Wigner function, spreading a wave packet, in solutions for bound states, in 1D scattering states, all that kind of stuff, and the studies we've been doing in recent weeks on the subharmonic oscillator. Okay, so that's all that stuff. All right, we'll discuss it more as the time approaches. All right. All right. So just to sum up what we were talking about last time, we talked about this idea of the quasi-classical states in phase space. They're also known as coherent states. And we obtain those states by a displacement, a phase-space displacement on the ground state of the simple harmonic oscillator. Okay? And that the phase-space displacement operator is a unitary operator which takes this form, or equivalently in terms of the dimensionless x and p variables, it looks like that. Okay? And the thing that's special about this state is that it is an eigenstate of the annihilation operator with a complex eigenvalue of alpha. Okay? So it's a kind of the closest approximation we have to a simultaneous eigenstate of x and p. Obviously, it's not a simultaneous eigenstate of x and p, it's an eigenstate of the annihilation operator. But the annihilation operator is this linear combination of x and p. So it's an eigenstate of that non-Hermitian operator, okay? And it has some very nice properties. It is, its expectation values are just the x and p values, though that's related to the real and imaginary parts of alpha. So it has its mean value is centered at x. It's in the x operator, and its mean value is centered at p. And moreover, it is a minimum uncertainty wave packet with equal amounts of uncertainty in x and p, just like the ground state of the harmonic oscillator is. Moreover, as a function of time, if the Hamiltonian of the system, I mean, I want to step back to say these states are a set of states that exist in Hilbert space, whether we're talking about a harmonic oscillator or not. Okay, they're just a set of states in Hilbert space, and we can talk about representation with respect to coherent states, regardless of whether we're talking about the harmonic oscillator. Okay, they're just those states. However, if the system is a harmonic oscillator, as to say if we're talking about a particle in a harmonic well, then if at time t equals 0, we started in one of these states, one of these coherent states, then at a later time, we stay in a coherent state. And the mean value, or let's say the eigenvalue of the annihilation operator, just evolves according to the classical trajectory. Okay? So x and t are just the classical harmonic motion of the particle. Let's just say, if I looked at this as a wave packet, then we start this as Gaussian state. The Gaussian wave packet just oscillates back and forth, exactly like the harmonic motion does, completely undistorted. I'm supposed to come back to that. Okay, so the wave packet is completely undistorted. It doesn't spread, it doesn't breathe, it doesn't do anything. It's just that wave packet that just goes back and forth in the harmonic well. As a classical particle would do. Okay? The other thing we discussed about these coherent states is that, of course, if they're going to have something that has a well-defined phase of oscillation, you kind of know where it is in what the phase of the oscillator is, then it doesn't have a well-defined number of excitations, right? It doesn't have a well-defined amplitude. It has to have some uncertainty in its answer, because there's a number phase uncertainty relation. And we saw that explicitly if we decompose this operator in terms of the number states. It is a superposition of number states. It has a mean number, which is the square of the amplitude, just like you would have classically. But it also has some fluctuations in the number of excitations. And those fluctuations we calculated were given by the square root of the mean. And that's characteristic of a Poisson distribution. And we see that explicitly if we look at the probability distribution of which is the square of the amplitude in the number basis, then that's given by this, which is the Poisson distribution. Okay. And in phase space, we kind of look at this and say, okay, what this state looks like is some kind of packet that's localized in phase space, right, around this value of x and this value of p, with an uncertainty bubble around it that's completely isotropic. And classically, it would just be this point in phase space. It's the pure state. We know exactly what it is. Quantumly, we can't define the state to have a definite x and p, but we can define it as a kind of minimum certainty packet that surrounds that point in phase space, okay? And it has this uncertainty, right? 1/2 or 1/√2 in the other. These root 2's fly around all the time. And this state is a minimum uncertainty in phase. Just looking at this geometrically, the number phase relationship is a minimum uncertainty.
Yep. You had the phase, for the alpha, you added time codes on the previous board. Adding that time codes into the summation is trivial, right?
In what way?
And just bringing it into the...
Sure, it's a linear operator, so we can bring that in. U of t, we can bring that in, and that's U of t on that. And then what is that? Good question. If it's a harmonic oscillator.
E to the I h bar t or h t over h bar.
Yeah, and what is, so that's e to the minus of ht over h bar on that, which is what? For this Hamiltonian.
From it in, what's that?
Yeah. So that becomes e to the minus I omega t n plus 1/2, right? And then, right? Now, of course, the overall phase I can factor outside here. I don't really care about that. So, putting all that back together, e to the minus I n, and then there's some overall phase out here that is irrelevant, right? But look at what that is. This can be combined with that. You get a new alpha, right? So this becomes alpha e to the minus alpha t to the power n over the square root of n factorial times, and I'll just put that in here too because I can. Doesn't change anything, right? And so that's exactly what we said, that u of t acting on this is equal to that, which is alpha t classically. Classically, the phase just rotates clockwise. So, well, that's not a good rotation. God, it's the worst circle ever drawn in the history of mankind.
It's a non-Euclidean circle.
Even womankind, any kind. Okay? So, that's why this is called a quasi-classical state. The center of the wave packet moves exactly along the classical trajectory. And moreover, its uncertainty about that classical trajectory is the minimum possible. Okay? And that is what makes these states quasi-classical states. But there's a little bit more to the story than that. I just want to conclude our discussion with one statement. I want to say a little bit more about the classical limit. What does it mean to talk about the classical limit in quantum mechanics?
What do you not do in quantum mechanics anymore?
So, yeah, you know, what do we want? In what way, in what sense is classical physics different from quantum physics? Now, there's lots of ways. And so there are lots of ways in which we talk about the classical limit depending upon which of those ways we're looking to match. One of them is we have classical dynamics. That is to say, one thing we might want to see in the classical limit is that we have, Hamilton's equation. Let's just talk about dissipation-free classical physics for a moment. We have Hamilton's equations of motion, Newton's laws, right? We might want in some way that the dynamical evolution of the system is described by Hamilton's equations of motion. That's one thing we might like to see in the classical limit. Now, we talked about this a little bit before. We know that we get this in the short wavelength. And WKB, we see some recovery of this, right? We saw that in the eigenstates, and we also saw that if we have a wave packet that is made up of a superposition of energy eigenstates that have short wavelengths relative to the scale over which the potential is changing, then we have geometric optics, and that geometric optics is Hamilton's equations. So that's one way we see that. The harmonic oscillator, though, is kind of special in the sense that for the harmonic oscillator, what's special about the simple harmonic oscillator is that the frequency of oscillation is independent of energy. If I take my oscillator, if I put it over here just a little bit, have it give that much energy, the period of oscillation is the same as if I started up here. I could go back. The period is exactly the same. The frequency is independent of the amplitude. That's special. Only the harmonic oscillator that does that. If I had any other potential, then this guy would roll down, come back. But that period would depend on where I started it. Okay. And we kind of see this, part of that is seen in the fact that the Heisenberg equations of motion are the same as the classical. We had x, the x dt, is p over n, and dp dt is equal to minus the spring constant, right? That's the force is minus kx. That's just like classical, and what that means is that no matter what wave packet I chose, the center of the wave packet will follow the classical trajectory. If I take the expectation value of this, the expectation value of this follows the classical trajectory. Of course, if at time t equals 0, the mean value is 0, then we never see any evolution at all, like as in the stationary states. But if I took any wave packet, it doesn't have to be the displaced harmonic oscillator, the displaced ground state, no matter what I chose, it will just follow the classical trajectory. So if I had some other funky thing, and maybe I have something that looks like this. It will follow the classical trajectory. If I had an ellipse around there, okay? If I had any shape whatsoever, because every point on this curve kind of goes around at exactly the same frequency. That's what I just said. So when we go around, it doesn't matter where it is, it goes around undistorted. So there's more than just the fact that the mean values follow the classical trajectories. It's more, we want more than that to say that something is classical, right? And that has something to do, there's another aspect that distinguishes classical from quantum, and that has to do with prediction of measurement outcomes. So in classical physics, we can assign a joint probability to both x and p. That there's some probability that I'll measure x and p. Classical physics, we would have a probability distribution on x and p. In classical statistical physics, that's what you do, right? That might be the Boltzmann distribution, if it's in thermal equilibrium, or if it's non-equilibrium, whatever it is, right? Okay? And the fact that we can do that means that we can calculate some, if we were to measure x and p, or x or p, we know how to calculate that from this probability distribution. And this probability distribution has some properties. These are numbers that are always positive, or non-negative, I should say. And we typically normalize the distribution to 1. In quantum physics, generally forbids this. The assignment of a joint probability. Because x and p don't commute. Now it's a little bit subtle why those two statements are the same, but they are. I mean, we know for one thing, if x and p commuted, then we could write down simultaneous eigenstates of x and p, right? And they would have both these. This would be a simultaneous eigenvector of x and p. And then we could define, some probability distribution on x and p as that. We could try to do that. But these states don't exist. There are no states that are simultaneously eigenstates of x and p, right? If I'd like to find a state that had this form, I cannot do it because x and p don't commute. Yeah, Stephen.
You said you wrote that generally, which implies there must be a case where they do with this cannon curve.
Yeah, we'll come to that in a moment. Set me up. So that, because this is not true, I can't do this simultaneously. I can't generally do this. Okay. Oh, now we do know, as you've been studying, there's this thing called the Wigner function. which I called a quasi-probability distribution. It has the property that it has the correct marginals. So when we talk about, this is the, if I have a joint probability distribution on two random variables, then the marginal probability distribution is the probability distribution for one of those random variables, irrespective of the other. So we said the marginal, the probability to have a certain value of x would be just summing over all other possible p values. That's the marginal of the distribution. And we demand that this equal, for a pure state, the square of the wave function. And the probability for p is the square of the momentum space. Okay. However, why is this quasi-probability? Because this thing can be negative. Which means that it doesn't represent the joint probability to find x and b, because the probability can't be negative. So one of the things that we would demand from classical limit is that in the classical limit, all the bigger functions are positive. And what distinguishes, in some sense, a classical state from a non-classical state is whether the bigger function is positive or negative. And this comes back to the question that Stephen was, when I wrote generally, I was hinting around the fact that there can be states where this is positive. In fact, you're doing one for homework right now. The coherent state. The coherent state is a state whose bigger function is everywhere positive. Yeah.
So for the little balls,
Yeah.
you know, I would expect it, I haven't
Yeah.
done homework yet, but just to be like just a nice little hill.
Exactly.
Okay.
Right. So let's take a, I'm going to give away the answer that you're going to derive from one, but let me just show you. I said, yeah, they're giving me the homework answer.
Wait, and you just a graph for the last part too.
Maybe. Come on, computer. Thank you. Let's see what we can see first. And then we'll decide. Oh, I need to turn it on, don't I?
I'll be done.
It is. It just takes a moment for the bolt to, yeah, I can see it. I can see the bolt.
Well, I saw the whole place out.
All right, there we go. Yeah, that's turn the light off. Oh, yeah. All right. So this is a picture from the website Quantum Optics, but it's the same view. So what am I showing you here? What I'm showing you are the Vega function. This is taken from a journal article. As a function of positional momentum here, position is called Q and P. Okay? And we're looking at this for 4 different states. Guess what this state is?
Ground state?
Could be the ground state, indeed. or any coherent state, which is just a displaced ground state, displaced to some mean value of Q and P. Okay? Notice, as you suggested, it's just a little hill centered at this. The Wigner function is everywhere positive here. Okay? So I can just think about this as if there were a classical distribution of possible complex amplitudes. I just don't know which one it is. This is another example of a state with a positive Wigner function. You know what that state is?
Squeeze state?
That's a squeeze state. A squeeze state is a state which is also a minimum uncertainty wave packet, but does not have equal uncertainty in X and P. Okay? And these are the marginals are being shown here. They are the projections onto the screen there is by integrating over all P, you get the distribution in X, integrating along X, you get the distribution in P, right? What is this state?
Looks like the unexcited state.
Yeah, which one is it?
Second.
Another guess. How do we know?
The number of peaks.
The number of nodes. Excellent. How many nodes does this have? It's got one node. Right? This is the square of the wave function. Right? It's not the wave function, it's the square of the wave function. And this is the wave function, square of the wave function in P, and this is the square of the wave function in X or Q, whatever you want to call it. Notice, in phase space, it's exactly what you would expect. In phase space, if I have the excited state, so here, you know, X and P, or Q and P, using their language. Here's the ground state. The first excited state had, stand in front of the door. Is localized around some circle, right? With that amplitude. So you would it must be that the Wigner function is rotationally symmetric around the origin in phase space. It must be. And that's what is being shown here. However, notice that this state is negative, right? And it has to be because there's no other way I'm going to get a node in here when I do the projection onto the X or P plane. It's got to be negative. So this kind of state is highly non-classical. And in fact, if I had a very excited state, even though the WKB approximation would have it peaked around the more localized near the turning points, in terms of its shadows of X and P, it would be really negative. Okay? It's only when I make a superposition that I can get rid of negatives. What about this guy? What's this? Something you might have seen in your homework. Close. Kind of like that.
Which homework was it? What did it say?
What's that?
Which homework did what it say?
Come on, you did the homework and you've read the solutions.
Oh, so
That's not a quantum, it can be a quantum harmonic oscillator, can it?
It's not an eigenstate harmonic oscillator. It is not. It's two.
Oh, could they be two different delta well? Or what she said?
Yeah.
That's what she said, okay. It was two Gaussian.
Two Gaussians, exactly. This is the Schrodinger cat.
Oh.
Meow.
That was a joke.
This is a state which is a superposition of being here with this position and this momentum, or being here with this position and this momentum. If I were a classical distribution, I would have some probability, some probability to be here, and some probability to be here. But because I'm in a quantum superposition of being here and being there, then I have quantum interference between those alternatives. And I have all this quantum weirdness in the middle. Notice, what is the, this particular guy is in a superposition of two positions, right? Okay? So it's in a quantum superposition of two positions. When I look at shadow on the position screen, well, has a probability distribution here or there, right? That's the square of the wave function. What does it look like in momentum space? It looks like that's that kind of thing. You know what that is? That's the double slit interference pattern, right? What you see, if I have a double slit and the particle is either here or there in some superposition, then in the far field, I see the Fourier transform. And the Fourier transform is the momentum space wave function. Right? So the negativity here is an indication of the non-classicality of the state. Okay? If we got to the classical limit, what we want is somehow these negative pieces have to go away, so that I'm left with just either this or that, rather than this in superposition with this. And there's no way we can get that dynamically out of just a closed system dynamic. To get rid of this, and we'll talk about that some point, we need decoherence. Decoherence is what gets rid of these negative fringes and gives us these two alternatives. We mentioned decoherence at the beginning of the semester, and hopefully we'll talk more about it as the semester progresses. But one of the messages that I want to take away from all of this is that one of the modern perspectives in quantum mechanics is to think about classicality versus quantum mechanics in terms of the statistics of the probability distribution of what you can measure. And moreover, how those statistics can be used as a resource for processing information. So a classical state, even though this is a state of quantum mechanics, for all intents and purposes, the statistics I would see if I did measurements would just look like classical Gaussian fluctuations. Whereas the statistics I would see from these guys would be nothing like that. Okay? And it's that distinction between what you can see in a measurement, what statistics, probability distribution can generate, is one of the ways that quantum mechanics is distinguished from classical mechanics. It's not just about Hamilton's laws versus the Schrodinger equation, it's about the intrinsic statistics of the measurements that you can make. The quantum harmonic oscillator, in some sense, is, always classical. Because it's linear, you always will, if you start in the ground state, you apply a harmonic force, you're just going to move this classical bubble around. To make something non-classical, I need something non-linear. All right. Very good. So, that concludes for now what we're going to talk about relative to the harmonic oscillator. Let's continue on the backboard and I feel like
say?
Yeah, let's turn off. All right. So we've been talking about the quantum. In talking about the quantum mechanics so far, we've been talking about 1 degree of freedom. We've been talking about spin 1/2, for example. In which case, our Hilbert space was the set of two-dimensional complex vector space, right? Or we talked about a particle moving in one spatial dimension, moving along the line. In which case, the Hilbert space was the space of square normalizable functions on a real line, right? That's what we've been talking about. How do we talk about more than 1 degree of freedom? EOF. Well, let's first review how we do that classical physics. Okay, how do we deal with that classically? Well, let's look at some examples. We might have 2 particles moving along the line. Right? They have positions and momentum. Or we might have a situation where we have 1 particle moving in a plane. Right? Those are both examples of 2 degrees of freedom. And the way we do it is quite simple. We have, if the phase space is what we call the Cartesian product. Of phase spaces for each degree of freedom. So if I have, x1, p1 for particle 1 and x2, p2, I take the Cartesian product of those 2 phase spaces and I have coordinates x1, x2, and p1, p2. Okay? That's the Cartesian product. And the total dimension of phase space is 2 times n, number of degrees of freedom. Now, of course, what coordinates we use is not unique necessarily. We have lots of choices. For example, in here I could talk about the position of particle 1 and particle 2. Or I might talk about the relative position between particle 1 and particle 2 and the center of mass position of the 2 particles, right? That's a perfectly good set of coordinates, and then there'll be a conjugate momentum to this, P rel and P center of mass, right? And I would just, and my, I would have then, you know, the relative momentum, the relative position as my description. That's perfectly good. Or in this guy, I could say, for example, instead of talking about the x and y coordinates, I can have the cylindrical radius scripty rho and angle. That's a perfectly good set of coordinates. And then there's a conjugate momentum, P rho, the radial momentum, and a conjugate momentum, P phi, which of course is the angular momentum. About the z-axis, right? So that's another possible set of, I can have r, p sub r, or r phi, I'm not r, rho, scripty rho, p rho, p phi. That's another one. It's a tensor product of those two spaces, not tensor product, Cartesian product. Okay? All right, so that's classical physics. What about quantum physics? So now let's talk about quantum mechanics, quantum description of multiple freedom. Well, let's, for example, just consider, for example, 2 degrees of freedom, e.g., 2 particles on a line, or 1 particle in a plane. Okay? And let me just call that I could call those 2 degrees of freedom having XA and PA and XB. A and B represent the 2 degrees of freedom. They could represent 2 particles, or they could represent the 2 coordinates associated with the plane. Okay? Now, of course, in the quantum description, these are operators. Moreover, so XA and PA satisfy the canonical commutation relation. As do for degree of freedom B. But A and B commute with one another. Now we kind of know that that has to be true. If we think about, for example, the fact that P is the generator of translations in position, right? So let's define the momentum. Let's just think about this in, for example, 2D. Right. So this is as an X component and a Y component. Okay. What we expect is that if I do a translation by some amount delta x on the x operator, I translate this by an amount delta x, where the translation operator you recall is e to the minus I over h bar p dot delta x, okay, which is approximately 1 minus I over h bar p hat dot delta x, and delta x is small. So if I look at that infinitesimal change over here, let's look at the ith component of this. The ith component. One plus I over h bar p j delta x j sum over j repeated in x. Yeah.
Should those x's in 2D space have carrots on hats on them?
No, these are numbers.
No, above. Up. Second line down on the left. Should it be x hat e to the x plus y hat e to the y on top?
Here, yes, indeed. Thank you. They should. So look at this. Minus I. And this is supposed to equal xi plus delta xi, displaced by that amount. And what do I get? I get xi plus I, or minus I over h bar xi comma pj delta x j sum over j. And so this must equal, if this is going to work, this has to equal I h bar, the Kronecker delta, delta ij. So what we see here is a general rule, as we'll understand more in a moment. Observables associated with different degrees of freedom commute. So I can simultaneously talk about the position along x and the momentum along y. Quantum mechanics allows that. Alrighty? So, what about the Hilbert space in this case for this particle moving in plane? Well, my defining representation were the wave functions. my wave functions, since I can simultaneously specify this 2 degrees of freedom, I can specify a joint amplitude for having XA and XB, such that this squared is the probability density to be near XA and XB, the joint probability distribution at the same rate. And I could talk about the joint momentum. Now, the position and momentum, so these wave functions, if they're going to be probability distributions like normalized, they have to be in the set of square normalizable functions on the plane. So this is the Hilbert space we're talking about. They're functions of 2 real variables which are square normalizable. Call this capital. Okay. And of course I can talk about the position and momentum space, wave functions related to one another through the Fourier transform. Right? And there's no reason I can't, in this case, because X and P for different degrees of freedom commute, I can write down a joint probability distribution that's kind of mixed. I'm going to know what got a half of the tilde on it? Maybe there's tilde on this part. I don't know what we would call it. We don't have a name for it, per se. But I could do this. There's no reason I can't. Right? That's to say this thing is I'm just Fourier transforming with respect to B. So I can write down a joint probability distribution by squaring this, joint for the position of particle A and momentum of particle B. It's not the same thing as the Wigner function, which had to do with X and P for a given degree of freedom. These are for 2 different degrees of freedom. All right. Now, there is a special set of states which are product states. Suppose that psi of x let's write it this way. Suppose that my joint probability distribution separates into a product of 2 functions. Okay. Then, of course, the joint probability distribution factorizes the probability particle probability density of this times probability density for that. Where this is the square of this wave function, and this is the square of this wave function. The product states are in some sense uncorrelated. That is to say, the probability of finding this has nothing to do with where B is. The two probabilities factorized. But not every state is of this form. Non-separable, which has a special name that we're going to discuss in much more detail later. They're called entangled. Entangled states. Suppose I have a state of the joint system, which is some amount of that product and some other amount of this product, where chi and eta are not equal to sine and phi. Then the probability distribution for this thing doesn't factorize. Okay? But this is in the Hilbert space. Because I can always take, if this is in the Hilbert space, this is in L up to of R2. And this is in L2 of R2. Then, by definition, any superposition of them is in L2 of R2. Okay? Now, moreover, every state in Hilbert space of our two-dimensional Hilbert space, not two-dimensional Hilbert space, our Hilbert space on the two-dimensional plane, can be made up of superpositions of product states. How do we know that? Well, let's look at a basis for this space. Yeah?
So you said every state can be written as a superposition of product states?
Yes.
Okay, I just want to make sure.
Yeah, so every state, that is to say every wave function in this Hilbert space can be expressed as some superposition of products. Not every state is a product state, but every state is a superposition of product
So
states.
they act like basis vectors?
That is to say, there exist basis vectors that are product vectors. Exactly. So that's what I'm about to say. So, for example, this is a basis. These are the simple harmonic oscillator number states. They are a basis for the Hilbert space on a line, right? So I claim the following is true. Well, before I say that, what does it mean to be a basis? That means that the set we know is complete. That is what it means to be a basis. right? And if I look at that, let's look at that. Let me look at this as in position representation. That says that the sum over all the number states, which are in the whole basis, un of x, un of x prime, is delta x minus x prime. That's what it means to be a basis. Now, I claim the following is true. Is a basis. On the plane. As I say, I could take a product basis of all the basis vectors for degree of freedom A, and all the basis vectors for degree of freedom B. How would I prove that? Well, what I want to be true is that when I sum over all these guys, both come from 0 to infinity, of this, it should be star, of course, but they're real, that's why I left it off. But I'll just write this more generally. But this should be a two-dimensional delta function. That's the completeness function. Let's say this is a two-dimensional delta function. Is that true? If I plug that in? Sure, it's obviously true, because it just factorizes. I have the delta function for A, and then the other sum is the delta function for B. So what this says is that I can form the joint Hilbert space as a superposition of product states from the individual degrees of freedom. And that has a technical name. It's called the tensor product. Not to be confused with the Cartesian product. We can explain. So what this says is that the Hilbert space L2 on R2 is equal to the tensor product of the two Hilbert spaces for each degree of freedom. So this is HA, and this is HB. And this is the joint Hilbert space of the two degrees of freedom. How do we define this formally? Well, let's talk about the Dirac notation here. So let's consider some Hilbert space, which I form as the tensor product of the two Hilbert spaces. Let's suppose I have a ket psi A, which is inside Hilbert space HA, and a ket phi in Hilbert space B. Okay. Then I'm going to define a product state, just like I did with the wave functions, but I'm just going to put this tensor product symbol in the middle. A state in the Hilbert space is obtained by looking at the tensor product between those. That's just like multiplying the wave functions with one another. All right? Often, sometimes we are sloppy and we leave out the tensor product symbol and just put them next to one another, but it is understood. We don't often always write the tensor product symbol there, unless we really want to emphasize it. Yeah?
Should that be B, not A? You have
Yeah,
A.
that should be. Sorry. Right. Okay, so how does this, what are the rules of the game? Well, the tensor product has the following kind of properties. It's linear. That's to say, if I take a constant, a scalar, complex number, and multiply it, that's equivalent to, I can multiply this guy, or I can multiply that guy. It's the same thing. The inner product. Oh, another part of linearity, of course, is that if I look at a superposition tensor product like this, that's the sum of the tensor products. Should have the A and B outside the case. Looks linear. The inner product. So let's suppose I have a product state. And I'm going to look at the inner product between this product state and this product state. That's just, you take the inner product on the first case, and you multiply that number by the inner product on the second degree of freedom. You know, that's exactly what you would have if you had two wave functions, right? I mean, it's very fancy notation, but if I had two wave functions that were psi 1 of xa, psi 2 of xb. So this is one wave function, and I look at the inner product of this with the other wave function, I want to look at the inner product between those two product states. How would I do it? I'd star this, multiply it by that, and integrate over the two variables, right? And that would factorize. I look at this integral and that integral. That's what this is saying in a more abstract form. Okay? Okay, and finally, the last thing I want to say about this is operators. So, suppose A is an operator that acts on Hilbert space A. It maps vectors in Hilbert space A to other vectors in Hilbert space A. And I have an operator B that acts on Hilbert space B. Then I can define an operator that acts on the joint Hilbert space of the two degrees of freedom. A product operator. So an example of a product operator is A tensor B. How does this operator act? It acts such that if it acts on a product state, then the first operator acts on this degree of freedom, and the second operator acts on this degree of freedom. Yeah?
So an operator can only act on an object that's in the right space, though?
Yeah.
You couldn't act that O way B on, say,
No.
an object just of A shape.
It doesn't, it's an operator has a domain. And the domain is defined by the Hilbert space upon which it acts. Now, we can be a bit, here's an example. Just to finish this last thought out. So let's consider a particle moving in xy plane. Okay. Now, if I write the x operator, that's the operator that acts on the x degree of freedom. Really, this is a shorthand for x tensor the identity on y. Okay? Because it's really a shorthand. We don't always write, and we rarely would write it this way. This would be incredibly pedantic, but I wanted to do it for a reason. Okay? And py, for example, really means the identity on the x-coordinate and the momentum operator on the y-coordinate. That's really what it really means. Now, why do these guys commute? Well, you see, because let's look at the commutator of x with py. Why do operators on different degrees of freedom commute? Because of this structure, right? This really is the commutator of x with the identity on y commuting with the identity on x and the momentum on y. That's what it is, right? So let's write that out. that is equal to X tensor identity on Y times identity on X momentum on Y minus the identity on X tensor momentum on Y times X tensor identity on Y. That's just writing out the commutator in absolutely gory detail. Okay? Now how do you write this? I didn't tell you that rule. I didn't tell you that rule, so I'm telling you. If I have A tensor B times C tensor D, that is AC tensor D. That follows just be how they act on the states. Okay, so now you tell me, what's this times this? So, this is X times the identity, tensor the identity times P, right? This times this, tensor this times that. Okay, what about this? 1 times this. This times 1. 0. Operators acting on different degrees of freedom compute, because they will always have the structure. Always. This degree, if it acts on this degree of freedom, it has the identity on all the others. If it acts on this degree of freedom, it has the identity on all the others. And the identity commutes with this, and the identity commutes with that all. So it's always the case that observables associated with different degrees of freedom commute. So for example, the spin, spin x, y, z don't commute, but the spin along x for particle 1 commutes with the spin along y for particle 2. It's only when they're on the same particle, the same degree of freedom. All right, we will continue this next time. Have a good rest of your day.